Welcome back to Unit 2.2, and in this video we are going to look at the extraction of iron from the blast furnace. It is 2.2.5 on your specification, and we're going to look at the different steps in the blast furnace, how we extract iron from its ore, and then we're also going to look at the uses of iron based on its properties. So we're going to look at the extraction of iron, and industrially this happens in the blast furnace. It's really important that you know the reactions that happen in the blast furnace in good detail, and this can be part of longer questions in the exam. We have looked at these reactions already earlier in this topic when we looked at reduction, oxidation and redox, but we're going to look at the specific reactions and the individual steps in a little bit more detail at this stage. So iron does not exist as just pure iron in nature, and so we have to extract it from its ore. That's how it's found naturally. The ore of iron is called hematite. That's a really important name to learn. Just be careful about the spelling. It's Haematite. Just be really careful when you're writing in that spelling. And it's mostly made up of iron oxide along with some other impurities, but it's iron 3 oxide. So that's iron with a valency of 3 bonded with oxygen, which has a valency of 2. So when we swap and drop that, we get Fe2O3. There are other impurities in the hematite ore of iron, which we'll come back to in one of our reactions in the blast furnace. But it's iron 3 oxide, so you need to know that it's Fe2O3. It undergoes reduction in the blast furnace using coke, which is a form of carbon. So you need to know first of all the raw materials that we use in the blast furnace. Essentially, these are the things that we put into the blast furnace in order to extract iron from its ore. So the first thing is the iron ore itself, hematite. It contains iron 3 oxide and sand. We also put in limestone, which is calcium carbonate. So the chemical name for limestone is calcium carbonate. And that is there to remove impurities. So calcium carbonate will react with the acidic impurities and remove them. And then finally we have coke or carbon. So coke is almost pure carbon, and that reduces the iron oxide to iron. It does that by stealing the oxygen from the iron oxide, and so it reduces the iron oxide to iron because it removes the oxygen. The loss of oxygen is defined as reduction. So you can be asked as a short question, what are the raw materials in the blast furnace? Or they might give you one of them and say what other 2 raw materials need to be added to the blast furnace. And so it's really important that you know those 3 raw materials and their general purpose within the blast furnace. So if you haven't already done so, please watch the other video that is attached in Google Classroom that looks at the blast furnace. Just think it's helpful for you to see the blast furnace, see the scale of it, see the size of it, and watch that process in action and hear that explained by someone who does this as a job from day to day. So if you haven't already done so, pause this video, watch that other video, and then come back to this. So what we're going to do now is look at each step in turn of the blast furnace. Again, it's so important that you know each step of these. You can explain what is happening and that you can write equations for each of these steps. So for each of the steps, explain what's happening and be able to write an equation to represent the process that's happening. This comes up all the time in past papers, so make sure you know this really well. So essentially just a broad overview first of all of what happens. So you can see from your diagram here that we put our 3 raw materials in at the top, and then at the bottom we put in some hot air. So we put a blast of hot air in at the bottom. You might think, well, why is that being put in at the bottom? Well, if you think heat rises, so when the hot air is passed into the blast furnace, the heat will rise. It will meet the iron ore, the limestone and the coke, the raw materials, and it will heat those up in order that they will react. And what actually happens is the iron oxide is reduced to iron, and that actually sinks to the bottom, and it's tapped off at the bottom. You can see here that it's tapped off and collected at the bottom. You can see on top of the molten iron, which is our desired product, there's also something called slag. And that's essentially our impurities, our molten impurities, which are run off as well. They are lighter than the iron, so they will float on top of the molten iron product, and they will also be tapped off. So that upper layer is always going to be your impurities of slag, because it is lighter. So it's on the top layer of what is run off, and the molten iron will sink right to the bottom where it is tapped off as well. So you could be asked to label that blast furnace. That has been asked in the past. So make sure you know that you put your raw materials at the top, that hot air is blasted in at the bottom, and that essentially the two things that you remove from the blast furnace at the bottom are slag and molten iron. Slag is your impurities, that's the top layer. Molten iron is your product, which is the bottom layer. So let's look at each of these steps in turn. So the first step is simply to add your raw materials, and we can see that we add the 3 raw materials at the top, and hot air is then blown into the furnace at the bottom. So step 1 is simply add the raw materials. So step 1 was just to add the raw materials. Step 2 is the production of the reducing agent. Now we said on the previous page that carbon is used to reduce the iron oxide to iron. That is true, that's what we add in to then reduce the iron oxide, but it's actually carbon monoxide that is the main reducing agent in the blast furnace. What we mean by reducing agent is something that reduces something else. So it's going to be the chemical that reduces iron oxide to iron. So that's important to learn, that carbon monoxide is the main reducing agent in the blast furnace. They could ask you that as a 1-mark question. What is the reducing agent in the blast furnace? So that's an easy question. And what's slightly more complicated to explain is how the carbon monoxide is produced, because we know that carbon monoxide is not one of our raw materials. Carbon is, and so let's have a look at how carbon monoxide is produced. It's actually a 2-step process. So the first thing that happens is, you've got to remember that the blast furnace is at an extremely high temperature. The hot air is blasted in at a temperature of around 1800 degrees. So that's a more than high enough temperature to burn the carbon that we add into the blast furnace. So if you think we've got coke, which is almost pure carbon, what happens when carbon burns in air? Well, it reacts with the oxygen in the air, and what does it produce? It produces carbon dioxide. Let's try and write a balance symbol equation for that. So if you can, pause the video and try and write a balance symbol equation for that. It's quite a straightforward one. So let's have a look. What's the symbol for carbon? It's C plus oxygen. What we need to remember is that oxygen is a diatomic gas, so it's O2. That's reacting to give carbon dioxide. You should know that the formula of carbon dioxide is CO2. If you're not sure where we get that from, we've got carbon, so that's C. Dioxide means 2 oxygens, so it's O2. That's a covalent compound, and they're named based on the prefix in front of their name. So carbon is just 1 carbon, dioxide means 2 oxygens. And that's a balance, that equation is balanced. We've got the same number of carbons and oxygens on either side of our equation. But we don't want carbon dioxide. We said that carbon monoxide is our main reducing agent, and so the reaction is not over yet. So at the high temperatures that we have in the blast furnace, we're continually adding coke into our blast furnace. And because we've got such high temperatures, more coke will react with the carbon dioxide that we've just produced, and that forms carbon monoxide. So the carbon reacts with the carbon dioxide that we've just produced in the first step to produce carbon monoxide. Let's look at a balance symbol equation for that. So carbon is C plus carbon dioxide, which is CO2. Essentially what happens is that carbon steals one of the oxygens from the carbon dioxide. So essentially one of the carbons moves from here to here. And so what we get as a result is carbon monoxide, which is CO. Mono means one, that means just one oxygen. So carbon, C, monoxide is O, just one oxygen this time. You can see our equation is not balanced, but if you think about that again, one oxygen moves from the carbon dioxide to the carbon, and so essentially what we end up with is 2 molecules of carbon monoxide. And you can do that just by simply balancing as well. You can see that on the left of the equation we've got 2 carbons, and on the right we only have 1, and so we need to put a 2 in front of our carbon monoxide. That also balances the oxygens as well. So that's step 2 of the blast furnace, is how we produce the reducing agent. So remember that carbon monoxide is the main reducing agent, but we don't just put carbon monoxide into the blast furnace. It's actually a very toxic, poisonous gas that binds irreversibly to your red blood cells and can cause suffocation because it takes the place of oxygen in your red blood cells. So we don't want to be dealing with carbon monoxide directly. And so what we do is we put coke, which is almost pure carbon, into the top of the blast furnace. Because of the high temperatures, it reacts with oxygen to produce carbon dioxide, and then that carbon dioxide reacts with more coke, more carbon, to produce carbon monoxide, which will then be our reducing agent, and we'll see that in step 3. Step 3 then is essentially the extraction of iron, and what happens here is the carbon monoxide reduces, it removes the oxygen from the iron ore to produce just iron. So we've got reduction happening here, the removal of oxygen from our iron oxide. Again, let's write a balance symbol equation for this. We'll write our word equation first of all. So on the left hand side of our equation we have our iron oxide, and that, remember, is iron 3 oxide. It's going to react with our reducing agent, carbon monoxide. So if the carbon monoxide is there to remove the oxygen from the iron oxide, what do you think is going to be produced? Well, if oxygen is removed from the iron oxide, we're going to be left with just pure iron, which is our desired product. It's what we want to extract from the blast furnace. But if carbon monoxide has stolen oxygen, essentially we're adding more oxygen to the carbon monoxide. It is being oxidized essentially. So if we're adding more oxygen to carbon monoxide, what is it going to become? It's going to become carbon dioxide. It's taking on more oxygen, so carbon monoxide becomes carbon dioxide. Let's have a look at writing the balance symbol equation for this now. What I'd like you to do is pause the video and try and write at least the formula first of all. The balancing of this equation is quite tricky, but pause the video and try and write your formula at least. So first of all, let's look at iron 3 oxide. What that means is we've got iron, Fe, with a valency of 3, and oxide is oxygen, which has a valency of 2. You just get that from the periodic table. We can't cancel those down, so when we swap and drop, we get Fe2O3. Then we're adding in carbon monoxide. What's the formula of carbon monoxide? We saw it in step 2 above. It's just simply CO. Carbon monoxide means 1 oxygen. That's reacting to give us iron, which is Fe, plus carbon dioxide, which is CO2. Now, as I said, the balancing of this equation is quite difficult. I wouldn't even do this by making my list. I would have a think about what is happening. So let's look at our iron oxide. We want to remove the oxygen from our iron oxide. How many oxygens do we need to remove? We need to remove 3 atoms of oxygen. When carbon monoxide steals that oxygen, how many oxygen atoms does it take on? It goes from CO to CO2. So you can see that it only gains 1 oxygen. Each molecule of carbon monoxide only gains 1 oxygen atom. We need to lose 3 oxygens from our iron oxide. So how many molecules of carbon monoxide will we need? We're going to need 3 of them. So let me say that again. We need to remove 3 atoms of oxygen from iron oxide, but carbon monoxide only takes on 1 oxygen atom each. And so we're going to need 3 molecules of carbon monoxide in order to do that. If we have 3 molecules of carbon monoxide, that then is obviously going to form 3 molecules of carbon dioxide. That's actually your carbon and your oxygen balanced. The last thing we need to balance is our iron. So you can see here in our iron oxides, we have 2 atoms of iron. And so we're going to produce 2 atoms of iron on the right hand side. We balance that by just simply putting a 2 in front of our Fe. You can make your list now and you'll see that your equation is balanced. That's one. Again, you get there eventually by making your list and putting your numbers in front of your formula. But I would say, and I never say this with chemistry, I would say this is an equation that you should just learn the balance symbol equation off by heart. So this equation here, learn it off by heart with the balancing numbers. Just simply because it's quite difficult. It would take you a long time in an exam to go from scratch. So this is one I would really recommend learning off by heart and learning those balancing numbers with it. But what you can see here is that we actually have a redox reaction happening, and we looked at this in the first part of this topic. If we have a look at what's happening to our iron oxide, so we start with Fe2O3 and that produces Fe. What is happening here? Our iron oxide is losing oxygen, and the loss of oxygen is defined as reduction. So our iron oxide is reduced to iron. But what is happening to our carbon monoxide? Our carbon monoxide is forming carbon dioxide. What is happening to it? It is gaining oxygen, and the gain of oxygen is defined as oxidation. So you've got reduction and oxidation occurring simultaneously in the same reaction. So this is actually called a redox reaction. Now, we sometimes refer to it mainly as a reduction reaction because the key part of this equation, our desired reaction as such, is that the iron oxide is being reduced to iron. So in terms of our iron oxide and our iron being produced, it's a reduction reaction. So that's why it says reduction in the top right hand corner. But if you consider also what's happening to the carbon monoxide, we can define it as a redox reaction. And so this step is essentially the key step, producing our iron, which is our desired product. And as we saw from our diagram, it sinks to the bottom because it is liquid iron, because the temperatures are so high in the blast furnace that our iron will be molten when it's produced. So it sinks to the bottom where it is tapped off. Again, that can be a question. How is the iron removed from the blast furnace? And you simply have to say it sinks to the bottom where it is tapped off. So that can be a 1 mark question. How is the iron removed from the blast furnace? It sinks to the bottom where it is tapped off. Or this could be asked as part of a larger question. This could be a 6 mark question on the blast furnace, asking you to describe all the different reactions. And there's one more part that we need to look at. And part of that, maybe one of the bullet points of your 6 mark question could be, how is the iron removed from the blast furnace? And simply, all you have to say is it sinks to the bottom where it is tapped off. So this is a really key step in the extraction of iron in the blast furnace. Really important that you can write that balance symbol equation, that you can describe what's happening here and how the iron is removed. And then lastly, we're going to look at how acidic impurities are removed in the blast furnace. We've called this step 4. It's kind of a separate step. It doesn't happen after step 3 as such, but it is a separate step. And essentially it would really happen at the start. So as we discussed earlier on in this video, the iron ore that we add is not pure when it is added. It's not pure when it's added. It contains sand, silicon dioxide as impurities. And so this is where our third raw material comes in, limestone. We've looked at how iron ore, the hematite, reacts, how the coke, the carbon, our second raw material reacts, and now we're going to look at how our limestone reacts and what is its purpose in the blast furnace. It's there to remove impurities, and again, you could just be asked that as a one mark question: what's the purpose of iron in the blast furnace? And it's to remove impurities, and it's because those impurities are acidic. Limestone removes these impurities by a two-step process. So it's a bit like producing the reducing agent. Within this one step, we've got two steps. And so the first thing that happens is that limestone undergoes a thermal decomposition. It thermally decomposes to form calcium oxide and carbon dioxide. Let's write the word equation for this first of all. So we're starting with limestone, and its chemical name is calcium carbonate. It doesn't actually react with anything else, it just undergoes what we call thermal decomposition. What that means is it breaks down using heat. So it undergoes thermal decomposition, essentially breaks down into smaller molecules using heat. And we're told in that sentence that it forms calcium oxide and carbon dioxide. So those are our products. So our word equation is simply calcium carbonate, arrow, calcium oxide and carbon dioxide. I know it looks a little bit funny in that there's only one reactant on the left, but that's because the limestone or the calcium carbonate does not react with anything else. It just breaks down in the high temperatures that are used in the blast furnace. So let's try and write the balance symbol equation for this. So first of all, for calcium carbonate, calcium is Ca. It's in group 2, so it has a valency of 2. Carbonate you will find on the back of your periodic table. Carbonate has a formula of CO3 2-. So we write down our formula first of all, CO3, and we ignore the charge at that stage. What we use the charge for is our valency. So our valency is going to be 2. Those will cancel out with each other, and so we get a formula of CaCO3. That's react to give calcium oxide. Calcium oxide, again, we've got a calcium with a valency of 2. Oxide is just oxygen with a valency of 2 as well. That will cancel out, and so you get your formula of just CaO. Plus carbon dioxide is CO2. And this equation is balanced. You can see essentially just your calcium carbonate is breaking down into 2 smaller molecules. So we have one calcium on the left and one on the right. We have one carbon on the left and one on the right. And then we have 3 oxygens on the left, and you can see there's 1 here in calcium oxide and 2 here in carbon dioxide, which is a total of 3. So that's the first step. The limestone essentially breaks down to form calcium oxide and carbon dioxide. And then it's the calcium oxide which reacts with our impurities. Calcium oxide is a base, and we know from our year 11 studies that a base neutralises an acid. And the impurities in the blast furnace are slightly acidic. We said up here that our impurities are mainly silicon dioxide, and we just write the formula of that in the same way that we would write carbon dioxide. Silicon dioxide means silicon, Si. Dioxide means 2 oxygens, so it's O2. So let's try and write a word equation for this second part of this reaction, removing the acidic impurities. So we have our calcium oxide, which we produced in step 1. That reacts together with silicon dioxide, which is our impurity, which we are trying to remove. And that forms something called calcium silicate. And here there is only one product. So essentially the calcium oxide and the silicon dioxide just bond together and form something called calcium silicate. That is also known as slag. So we saw that at the bottom of our blast furnace. Again, it is molten in the blast furnace because of the high temperatures. It sinks to the bottom where it is tapped off, just like the iron is. But if you remember back to the diagram, the slag is the top layer. So that's another name for calcium silicate. Let's try and write the balance symbol equation for this reaction. So calcium oxide, we saw in the equation above that it is CaO. It's reacting together with silicon dioxide. Again, remember that's just silicon, Si. Dioxide means O2, 2 oxygens. That's reacting together to form calcium silicate. The easy thing about this equation is essentially everything just merges together. The formula of calcium silicate is just Ca Si, there's our silicon, and then our oxygens are all together. You can see that we've got 1 oxygen in calcium oxide and 2 oxygens in silicon dioxide. So that's a total of 3 oxygens. So your formula of calcium silicate is CaSiO3, if you just remember that it all merges together. So essentially in step 1, our calcium carbonate breaks down into 2 smaller molecules. Our CaCO3 gives us CaO plus CO2. And in step 2, it's almost like the opposite. 2 smaller molecules bond together and form a bigger molecule. Calcium oxide, CaO, reacting with silicon dioxide, SiO2, to form calcium silicate, CaSiO3. Again, you need to know those 2 equations. This can be a 3 or 4 mark question. You could be asked to explain how acidic impurities are removed from the blast furnace, including equations. Or again, it could be part of a longer 6 mark question where you're asked to explain all of the steps of how iron is removed from the blast furnace, including how acidic impurities are removed. So you need to know these 2 key equations as well. And as we've already said, just as with iron, the slag or the calcium silicate sinks to the bottom where it is tapped off, just with iron, just as with iron, but the slag is the upper layer. So the slag, which is not actually green, but just for this, to demonstrate this, slag is the upper layer. It will float on top. The molten impurities essentially float in the top, and the iron will sink to the bottom. It will be the lower layer, and it will be tapped off separately. So that's essentially the blast furnace complete. So we've looked at the different stages of how iron is extracted from its ore in the blast furnace. I would recommend doing a revision sheet on the blast furnace alone. It is asked all the time in exams, so it's really important that you know it in great detail and can answer the questions that are asked. It could make up a good 10 marks of your paper, so make sure you know it really well. So let's just run through it again really quickly. So the first thing we do is we add our raw materials. That's the iron ore, which is called hematite, which is mainly iron oxide with some acidic impurities. It's the coke, which is carbon, and limestone, which is calcium carbonate. Then we've got the production of our reducing agent, which remember is carbon monoxide. So we start with our coke, and at the high temperatures, it reacts with oxygen to produce carbon dioxide. And then that carbon dioxide reacts with more coke to produce carbon monoxide. And we need to put a 2 in front of that carbon monoxide to balance it. Our third step then is the reduction of our iron ore. Remember, our iron ore is mostly iron 3 oxide, which has a formula of Fe2O3. That reacts with our reducing agent, which is carbon monoxide, CO. The iron oxide is reduced to iron, which is Fe, and as a result, our carbon monoxide is oxidized to carbon dioxide. It steals the oxygen. Because we have 3 oxygens to remove from our iron oxide, we need 3 molecules of carbon monoxide. That produces 3 molecules of carbon dioxide. And we also produce 2 molecules of iron, since the formula of iron oxide is Fe2O3. And then lastly, we've got the removal of our impurities. Limestone is responsible for removing our impurities. That's the raw material that we use to remove those impurities. Remember, this is again a 2-step process that the calcium carbonate, which is limestone, undergoes thermal decomposition to produce calcium oxide and carbon dioxide. That calcium oxide then goes on and reacts with our acidic impurities, mostly silicon dioxide, SiO2, to produce calcium silicate, which is just merge that formula together, CaSiO3 in total, and that is what we call slag. And the slag and the iron sink to the bottom where they're tapped off. Slag is the top layer, the molten iron as the bottom layer. So what I'd like you to do is to put together your own revision sheet for this. You may do a sketch of the blast furnace and label the the different steps around the blast furnace. What you really need to have on that is definitely your balance symbol equations. Make sure your raw materials are clear as well. But those are the main steps. You need to be able to explain them as well as write balance symbol equations for them. And then very lastly, at the bottom of page 27, it's just looking at the uses of iron, which is a separate point on your specification, but it's very, very brief. And just that we use iron in construction, in many structures and bridges due to its strength, but also because it's a relatively cheap material, because the iron ore, which hopefully you know by now, is called hematite. Be careful of your spelling of that. It's HAEMATITE. So hematite is abundant. That means there's lots of it naturally, and so therefore it's a relatively cheap material, and it's used in structures including bridges and many other buildings due to its strength. So you may be simply asked, why is iron used in construction? And it's simply because of its strength and because it's a relatively cheap material, because the iron ore hematite is abundant. And then the last thing I want you to do to finish off this topic is to complete questions 1, 2 and 3, which are on this page, page 28, and your next page, page 29. Do that in your blue book or in your on file pages. Just make sure your title is the blast furnace or questions on the blast furnace. Make sure you have your revision sheet done first of all on the blast furnace if you haven't already done that. And please do so now, and that will actually help you then with these questions. They should be straightforward enough. I know the blast furnace can be a bit complicated, there's lots going on, but just make sure you go over those key reactions again and answer these questions as fully as you can. There should be none that you're leaving out, because all of that information is in your notes, so use those few pages in your notes, or watch that other video as well again to help you understand the processes that are going on. And that then finishes us with this topic of redox, rusting and iron.